to have sunspots to help us when we working DX, right? But there's no sunspots. We're at the very low minimum of the sunspot cycle, and you can see it here. Matter of fact, this is kind of a really strange low minimum where we are right now, because you can see that the last, 6 or 8 points on this graph is basically 0. It's rather a low minimum. We're going to talk a little bit about sunspots, but we're also going to talk mostly about solar wind tonight and what that's doing for us right now when we don't have these sunspots. If I try and turn off some of the lights, you think it would be better to look at the screen?
Yes.
Yes.
Let's see what we can do.
Perfect.
How's that?
That's great. More better.
More better.
More better.
More better.
So, let's see. So tonight's talk is about solar wind from a spotless sun. And this solar wind does some interesting things, and it's good to know a little bit about it during this period, because we're going to be stuck with this for another, 3 or 4 years before we really get some good sunspots. Well, if we're working DX on the HF bands, certainly, bands like 20 meters, 15 meters, 10 meters, the sunspots are important, but we don't have them. So the question is, what else is going to happen, or what else does happen when we're dealing with HF propagation? Well, we know what sunspots are. Basically, they give us the intense UV light, and that ionizes the ionosphere, and that bends the HF waves when they hit the ionosphere. It's really refraction. It's not reflection. Technically, it's refraction. Bends the waves. They come back down, and we can work some DX. But without that, we still have a little bit of UV. The UV we usually get from sunspots is very strong, very intense, and really ionizes the ionosphere. But the UV we have now is kind of minimal. So you've seen this chart, this one that I have here. You've probably seen this in some web pages. But this chart, although you can't read it maybe from where you are, has some very interesting information. First of all, it has the solar flux. In this case, it's down around 68. This was November 17th. And sunspot number is 0. Yeah, sunspot 0.
Wow.
But this number here underneath it, 304A, which is 304 angstroms, is the wavelength of the UV that's most essential to ionizing the ionosphere. And they give a number, and this is measured at a satellite called EVE. These are 2 different numbers of 2 different satellites. But if you watch this number, 152, when we get sunspots, it really starts to go up, and that's what we're interested in. So you can look at this data every day. They publish it, and you can get this detail. I have some websites at the end of this presentation to talk about, but you can find this pretty easily. So that's basically what the UV is. Well, let's talk about some of the other things. What do we have left if we have no UV and no sunspots? Well, we do have magnetic field disturbances, and this is the geomagnetic field of the Earth. And we get that disturbance from solar wind, and we get it from CMEs. What's a CME? Coronal mass ejection, where a lot of material is ejected from the sun, from the corona on the sun, and often, well not often, but occasionally it heads towards Earth. So we have a constant solar wind and occasionally these eruptions that will send material, and the material is basically atoms, molecules towards Earth, and they're ionized, and we'll talk more about that. We have radiation storms, and that's also part of solar wind and CME, and this is about particles. This is like ionized hydrogen atoms, helium atoms, those kinds of things. And they have a pretty high energy level, 10 megaelectron volts. And the radiation here is real radiation. This is stuff that can affect every living thing. It's like it's not nuclear radiation, but it's similar in a sense. If you know what the alpha particles are from nuclear radiation, this is similar to it. And then we have also radio blackouts that occur. And you even have these without sunspots. We have solar flares, and solar flares are basically the X-ray radiation that comes out in a burst from the sun's surface. And that is so intense, the X-ray radiation can be very intense, and it will hit the Earth and ionize the D layer, causing a radio blackout. And I've I mean, probably a lot of the guys that have been on the air for a long time have been operating, and you can actually hear this occur over a few minutes. Sometimes the band will go completely dead. All right, well, I think you've seen this picture before, but what is this picture really telling us? All these lines represent the solar wind coming from the surface of the sun. And it's a continuous solar wind. It does vary a little bit. You don't need a solar flare to cause solar wind. Solar wind occurs naturally, continuously. It hits the magnetosphere of the Earth, the magnetic field, and some of the particles will be actually brought into the poles of the Earth. And that causes what? Well, very often those particles are causing the aurora. But they also hit this magnetic field and change the shape of this magnetic field. And that's what causes us some of our problems. Now this is somebody that you've probably seen if you've looked on the web at some of the information. This is Tamitha Skov, and she's a scientist that deals with weather, but space weather. She reports space weather about a weekly basis. And I've got some of her information in this tonight. We're going to talk a little bit about it. But we have no audio. That's good. So let's see what we're going to do here about the audio. I don't know how I'm going to get that back exactly. Yeah. Well, we have our audio here. That's good. Shouldn't be 100. Let's see. Can I play from here? No. Okay. Right there.
Yeah.
Let's see. That won't do it. And there's no audio for that. So I guess we're not going to have audio tonight. Okay. Well, then I will continue, and I want to point out a few things about what Tamitha reports on. And basically, some of her reports are about solar wind and the holes in the, which we can hardly see here, but there are dark regions of the sun's surface, and that's where the solar wind is emanating from. It comes out of those dark regions. The solar wind that will hit the Earth is basically the regions that are facing us. There are regions, North Pole and South Pole, which are pretty much holes in the corona, but the ones that come across the equator are the ones that really face Earth. And if you look at how it's done, well, of course the sun turns at 27 days, or every 27 days it rotates. So the solar wind that might be coming out of one of those holes in the corona will kind of be sprayed out sort of like a water hose if you're turning around in a circle. And when it hits the Earth, that's when we have our problems with it. Another thing Tamitha talks about is these satellites in orbit, and they are in orbit approximately from the orbit around the sun, approximately as far as the Earth is. And there's an A satellite and B satellite. They're called stereo satellites, and they will actually take pictures of the sun in real time, transmit them back. And this is one of the pictures from stereo A right here. And what the advantage is here is that you can see things that are on this side of the sun as it rotates, and that will be facing Earth in a few days later. So you can see what's coming, and that's the whole idea behind these stereo satellites, A and B. The B side is the sun spinning away from us, but it's also interesting for the scientists to look at that stuff as well. You can see on the top here it's a little darker, and on the bottom it's a little darker. That's also holes in the corona where you're getting much more solar wind, but it's not directed towards us. Another thing that she points out is that occasionally this is a disk that represents the sun being blocked out and the corona around it And this is a CME, coronal mass ejection, that happens from an eruption on the sun. And this one is going straight out, and it, when she talked about this, it does impact the Earth, as a matter of fact. This one does impact this. So it's an interesting thing. If you get on YouTube, you can see her presentations. Now, she also gives us this information, and it's broken into two pieces, the upper latitudes and the mid-latitudes. And we're basically in the mid-latitude here. All of the U.S. is. And in this case, she's talking about solar storm conditions and aurora. Well, the solar storms here are material coming in, the particles coming into the Earth, and they come in either from the solar wind or from this coronal mass ejection, CME. And then there's a forecast, and the forecast here is for Halloween and November 1st, 2nd, 3rd, 4th. Official NOAA forecast is the first 3 days, and she extends it out 2 more days. But when it says unsettled, that's the magnetic field of the Earth. And it's unsettled because the solar wind's hitting it. And with unsettled conditions, transmission, bouncing our signals off the ionosphere is not very good when it's unsettled. And it's even worse when it's called active. So there's an active level of maybe 15%, and decrease it to 10% here. But you've got a situation where, yeah, you can still get on the air and make contacts when it's unsettled, but when it goes to active, then it's a little difficult to make DX contacts using skip on the HF bands. Well, in this case, she also predicts some other things. And this is the solar flare and particle radiation. Remember I mentioned solar flares before and particle radiation. Now solar flares are basically X-rays, and X-rays are actually talked about in different class levels. And if you have an M class or X class, it will affect propagation here on Earth. So the M class flares are, yeah, they're pretty much something that'll disturb everything. An X class flare will really clamp down on all propagation, and that's when you get radio blackouts. So in this case, M class flares are only 1%, so really it's not going to be a big problem during this period of time. You know, the ionosphere will be pretty good, other than other things coming in like the CMEs we talked about and some of the solar wind. So basically the sun's spotless during these days, and she has the solar flux prediction here as well. So it's pretty interesting to get on YouTube and bring this up and you know, find out a little bit about what's happening in the next week or so, especially prior to contests. So this is helpful. Now this bottom part here is the particle radiation, or what they call particle radiation storms. That's the particles I talked about before, which are really, can be dangerous. And dangerous to frequent flyers, especially airline crews, flying in high latitudes. You know, on that trip from, let's say, New York to Tokyo, you're flying over high parts of, northern parts of Canada and Alaska and things like that. If you make that trip continuously, you've got to be a little careful because you can get a pretty good dose of radiation. And especially for PN, that's prenatal. So if a woman is pregnant and flying, that's a good thing to pay attention to. That's a route you probably don't want to take. All right, what else we got here? Tamitha talks about the disturbance in the magnetic field. And we all know what the K number is, the K index. If you've worked on HF, you're interested in what the K level is, or K index, because that shows you the amount of disturbance in the magnetic field of the Earth. And when it gets up to level 4, it gets pretty difficult on the HF bands. Level 3 is, yeah, it's not great. If it's 0, 1, or 2, that's what we'd like to have. That's really the best conditions. And they've been pretty much in the 1 and 2 range over the last couple of months, as far as I've noticed. This was a particular day. This is October 25th, 6th, and 7th. and a storm was hitting, and you really had conditions go up to 6 and 7, I think, up here 6, yeah. So that would be a period where it's not great to operate. And this is hourly measurements, by the way. You can even find this stuff in real time. They update it every minute, some of this data coming in from the satellites.
Ed?
Yeah.
So what you're pointing out over here is, let's say during the contest, when all of a sudden the band goes dead for an hour, that's what's causing it.
Yeah, it could be. It could be this. It could be. Now, this is the disturbance in the magnetic field, and definitely it causes a difficulty in propagation at that point. The other thing is you could have an X-ray flare and ionize the D layer and just shut down all RF trying to go up to the F layer. It just blocks it all out. We get D layer ionization every day on the sun side of the Earth because of the little bit of UV that's coming in. It ionizes the D layer, the lower layer, and that prohibits 80 meter, 160 meter operation. You don't get anything going up to the ionosphere on those frequencies at that point. But yeah. So this is another picture of the same thing I showed before, but I want to show a little bit more about it. This solar wind takes the magnetic field of the Earth and actually distorts it and pushes it way out into space. This tail goes way out. You get most of the particles deflected, and if they weren't deflected by this magnetic field, we wouldn't be here. This would be just too much radiation for us. You have some of the particles here go into the cusp, and as I mentioned before, it causes the aurora around the poles. And you have the Van Allen radiation belts, this lighter green, and they are really electrons that are circulating back and forth from what I've understood. I'm not the credentialed expert on solar activity, but from what I have read over the years, the electrons really circulate in these radiation belts, and that causes, as this magnetic field is hit by solar wind, it can fluctuate and change. And how fast can it change? Well, it can change instantly because the solar wind is not a pure, steady flow. It's kind of clumped together and what is the solar wind, as I mentioned? It's ions, particles, and as those clumps hit the magnetic field, they change it. And when it gets intense, they are modifying or changing the Earth's magnetic field, and in the same way, that changes the propagation through our ionosphere of our signals that are bouncing off the ionosphere. So they actually will disturb the ionosphere pretty quickly and cause things like fading and dropouts and things like that. So if you have a lot of QSV, could be one of the conditions that's occurring. That wind can be hitting that magnetic field, disturbing it pretty rapidly. All right. Yeah, go ahead, Richard.
How far out does this magnetic field flow? I mean, how from the distance from the Earth? What's the area of the magnetic field? Did you know?
I think what I read was it was like 6 Earth diameters, something like that. So it's in that magnitude. And I mean, theoretically, the magnetic field, if you had sensitive enough instruments, you could measure it out to, probably forever, because it's a magnetic field, and a magnetic field, if it changes, it propagates. And like our radio waves propagate around the world, we bounce off the ionosphere, but also in outer space, radio waves travel almost infinitely, right? What happens, of course, is the power in that wave, or the intensity of the wave, decreases with distance, so after a while you can't measure it unless you had a very sensitive instrument, but at some point you can't measure it at all anymore. So it does, and as a matter of fact, the sun has its own magnetic field because it's got poles, and that magnetic field of the sun is what happens when we have solar flares, and the solar flares have the magnetic fields come up through the hole of the sunspot and causes an eruption. So there's a lot of things going on with the sun itself, and those magnetic fields are very intense, of course.
Are we at 90 degrees from the sun's poles?
Just about, yeah, just about. And so we are, yeah, just about at the equator. So when we look at sunspots and the holes in the corona for the solar wind, we're always looking at the equator. That's where we'll get our best guess at what's going to happen. This is another page on the web that's very useful, solarham.com. And it's put together with the highlights of information from other websites, which are very, very useful if you want to look at what's going on right now. You can find your K number right here. You can find the proton particles coming in, what levels they are. You can find your X-ray flares here. And in this case, they're very low. These lines show that they're very low in class A flares, probably, which are nothing. It doesn't bother us at all. But if they're up here in class M and F and X, they're very intense and they will disturb everything. Gives you some pictures. You can see where a CME might be occurring as well. This is the data I showed before with the the solar flux and also the UV information. So that's an important thing. And you can go on and look at that for hours. It's an amazing thing if you have any interest in this. Now this chart is updated once a minute, and this is one of the most interesting charts that I have run across. But it's basically real time, and it may be difficult to see, but what I'm going to point out is this is the magnetic field on Earth, and it's pretty constant here. It's not showing too much disturbance. This is the density of the solar wind. And when I say density, it's how many particles per, measured any way you want, cubic feet, cubic centimeters, whatever. So it has to do with how much material is coming at us. When this starts to rise, you can see that the solar wind is getting more intense. I should say over here, right in this area, matter of fact, you can see it's starting to rise, and so it's getting more intense. Now this one, right below it, in the yellow, is the speed of those particles in kilometers per second. And that's usually coming at us at a couple hundred kilometers per second. And you can see the speed is increasing. Now the timeline here is by days. This is December 5th, one day, and this is December 4th. So you can see what's happening just about in real time. And the last part is the temperature. Why is the temperature of the solar wind important? Because that shows you how much energy is in those particles. When the particles are hot, they're moving much faster, they're vibrating, and they have a lot more energy in them. So we look at these three different things, the density, the speed, and the temperature, to get an idea of how much is going to affect the ionosphere or magnetic field. And you can see at this point the speed is increased, but the one thing I want to show you is that there are two vertical lines here. Okay? And this is actually a forecast, because the first vertical line is the satellites in space taking these measurements. And the second line is 1 hour later on Earth, which is forecast forward 1 hour later. So what you have is what's going to be happening in the next hour. And again, this is of interest to nerds that like to think about this stuff, but it's also, if you're going to do some contesting, this is another thing that can show you, oh, that's why I haven't been able to make any contacts in the last 20 minutes or whatever. One of the things that you see here is this big spike. Well, what is this down here? Okay, well, this is the K index. This is the K index we talked about before. And you want a K index of maybe 1, 2, maybe 3, but if it goes up to 4 or higher, you don't get very good propagation. So that's another element to look at here. And this is the disturbance, the magnetic field disturbance, which is what causes us to have very poor propagation. And there was some event here that happened at this point in time, and you can see how the K number went up and it decayed after a while. Right here in this area where we see the speed increasing and the density increasing, we know that the solar wind coming in is a little, getting a little aggressive, and you can see the K number coming up in the magnetic field disturbance. So this chart is kind of interesting. You can find it in many places. Some of the websites available, like the websites from NOAA, from the Space Weather Prediction Center. There's a couple of government sites like that are pretty good. Just wanted to add a little bit more about Tamitha Skov. She's basically the space weather forecaster, and she's helping a lot of the public understand what's going on with space weather. People who are interested in aurora, people that use communications, maybe emergency services and other things. Also for your GPS. The GPS is really affected by some of those electrons coming in with the solar wind. And it's a funny thing, a couple of weeks ago I was out in Fort Lauderdale, had my car parked in a parking garage, and I have my 2 different programs on my cell phone, works on GPS to get back to my car. It's got the location of my car, right? Well, that day I got there and I opened up the first program, and it showed my position was like 2 blocks away from where I really was, and therefore my car position wasn't going to be accurate either. I opened up the other program, the same exact numbers. I'm saying, what's going on? Yes, sir.
Quick announcement, we got a Nissan car over here that's blocking some folks in, right on the end of the handicapped area.
Yeah, there's only one car
What
parked
color?
in the handicap area over here.
Yeah, what-
We need to get a truck back into there, and
Here's Marty. All right, thank you. Sorry, Ed.
Yeah, no problem.
thank you guys.
Well, anyway, I gave up on computer programs on my cell phone to try and find my car that day. I did find the car though. Okay, so anyway, Tamitha, she works in the fields of solar space physics research and testing spacecraft materials in realistic space radiation environments. So it's something that is pretty interesting from her point of view, although she doesn't talk about her work in her presentations. Basically, she does just talk about the weather forecasting, the solar weather forecasting. And she's known as a space weather woman. If you look for her on, search for her on YouTube somewhere.
She is a ham, Ed.
She is?
Yeah, she just got her license.
Yep, she just got her license.
Oh, great. Oh, I didn't know that. See? Okay, I learned something. Cool. Yeah. Just to finish up, these are basically the takeaways from our discussion tonight is the solar wind is always with us. And it doesn't help us, but it does affect the propagation we have here. When fast enough and dense enough, yeah, it disturbs the geomagnetic field, raising the K index, and it'll cause all kinds of fading in QSB and other things, especially when it's higher band use, the maximum usable frequency, the MUF, is kind of depressed. Causes aurora, and it's similar to CME. So the solar wind is similar to the coronal mass ejection because they're both made of plasma particles. It's just that the CME is a real burst, and it's usually very dense, and it's much faster, so it has a bigger effect when that hits the Earth. The solar wind is traveling at several hundred kilometers per hour. It may take a couple of days to reach us. If it's a slow wind, it may not have much effect. It may take 3-4 days to reach us. If it's a fast wind, it might be 24 hours. So that's something to watch. Excuse me. The speed of the solar wind is probably one of the most important factor of how much it will affect our ionosphere and magnetic fields. So the energy, as we talked about before, is the temperature, the density, and the speed. So that's pretty much it. So that's the presentation I want to talk about, and I have a couple of these websites here, and if you're interested, you can see this is Space Weather Prediction Center at NOAA, and Tamitha's website. You can find the information there, and also solarham.net. So that's pretty much it. Yeah, if anybody wants to get a picture of this, you can go up and take a picture. Yes, sir. Go ahead, Rick.
I got a question.
Yeah.
The bands are either long, you're talking to New York,
Right.
and you can't hear anybody in Florida,
Right.
or you're talking to somebody in Florida and you don't hear Texas.
Yeah. And what band are you on?
39,
Yeah. 80 meters.
75, yeah.
Yeah. Well.
What's the deal, man?
Well, at night, right? At night, the D layer, which is above us, but not as high as the F layer, which we use for sending our signal up to skip down. The D layer at night is almost completely gone because there's no UV illuminating
Nothing
it
to
to.
refract the signals.
So what you have is our signals will go through, past the D layer, up to the F layer, hit that, be refracted down, and you will get long conditions on the band. You'll be able to talk to New York, okay?
Okay.
But as soon as the sun starts to come up, and remember, the Earth is kind of rotating into the sun, okay? So as soon as that sun starts hitting that D layer, starts to ionize it, and you lose your long distance stuff. But what you get is you get more NVIS, so you get all the local people. And, you know, Sunday morning, I'm on the band on 80 meters.
I hear you.
And I've got, we have a net for Florida, and we start off by hearing everybody from, you know, Pennsylvania and Illinois and South Carolina, and then as soon as the sun starts to come up a little bit, all of that goes away, and we can only hear the local guys. So that's, you know, it depends a little bit on what band it is too, as to how that happens. It's opposite in 20 meters, right? 20 meters during the day, when you start to get the sun and the UV ionizing the F layer, you get a fair amount of skip. So 20 meters, you know, midday is great for working Europe or maybe South America somewhere.
South Africa.
And Africa, yeah, I worked Africa this morning, matter of fact, South Africa on,
But sometimes at night, there's no sun,
right.
at least not that I know of. Sometimes you get close bands, sometimes you get nothing.
Yeah, yeah, you can get nothing, and you know, that's part of what I mentioned, the disturbed magnetic field can cause real problems even at night, and you won't get anything there.
And
So
then
this
you
is,
come back 2 hours later and the band's over.
yeah,
Wide open.
yeah.
Yeah.
Yeah, there's some dramatic change that take place. I've heard the bands, I've heard signals on the band, and I've heard it shut down within 5 seconds. Because of a solar flare that just was an X-ray flare and just blocked out everything. It's amazing. Other questions? Anybody else?
And all of a sudden they're gone.
Well, I thank everybody for paying attention, and hopefully